Okay. Hello again. My name is Bob Kizek, and I'm going to run the presentation today, the Friday WebEx. Today we've got something pretty exciting, another new product coming out. This discussion is going to be on the IRM 11 refractometer. Now, as we we review the mission statement for Anderson-Negele, and that's to provide complete sensor solutions and services for hygienic process engineers in dairy, food, and pharmaceutical. And the IRM very nicely laces into that mission statement in that it's a new sensor providing new solutions for our food processing customers. So there it is, introducing the IRM 11 inline refractometer. All stainless steel. If you can grab the perspective, that's a 2-inch tri-clamp, so this is a fairly small device with an M12 connector pictured on it. To jump into the meat of this conversation, I'm going to go into the principle of operation. So much as we have been telling you about the virtues of turbidity for the last 5 years or so, and turbidity being a measurement of undissolved particles in a media or in a product, the refractive measurement or refractometer is now going to look at the effect that dissolved solids have within a liquid. And so it measures, it measures in a liquid the refractive index. And if you look at the picture on the right depicts how the how the refractive index is achieved through the interface of two media. So this below portion is a water, and the above is the air. And what we're doing in this picture, in this image, is we're sending a light beam at an angle into this interface. And what occurs when that light hits the interface between those two different density medias is it's going to deflect off at an angle. So it's no longer going to continue in a straight line. It's going to go and off at a slight angle. That deviation, that angle of change that occurs depending on the media differences is what's referred to as the refractive index. So what we now have is we're going to have a sensor that is going to determine the effect dissolved solids have within the liquid in the way in which light moves to it. Understand that in our device, all of this is internally done, so as far as there's no light penetrating deep into the product stream, everything occurs with a very small layer of liquid on the surface of the lens. But nonetheless, it is still a refractive index measurement. Now that change in refractive index, that directly correlates to the change in the media, whether we increase or decrease the amount of dissolved solids or components within that liquid. And so we can now look at the concentration of sugar in a liquid, in a water. So if we were looking at a sucrose product, we could now determine how much sugar resides within that sucrose liquid. Now we take that and we couple the refractive index measurement, which is the deflection of the light as it passes through that difference, and we take it and couple it with a temperature measurement within the sensor and some sophisticated calculations that are done on board. And what we can do is then calculate the concentration of sugars or salts or other components that are dissolved within that liquid. Keeping in mind that all of that, all those percent calculations or concentration calculations are still based on the refractive index, that measurement of the light change. So the IRM key features, you know, if you talk to people who have experiences with refractometers, they tend to be large, two-component devices, a bit bulky. The IRM is very small, all-in-one integral design. So you've seen a lot of this coming from Anderson-Negele in our product designs, is we tend to want to make them more sensor-like. So we make it compact, make it simple. So making it all integral means we don't have cables that we have to, cut and wire to panels on the wall. We have a device with an M12 connector, and we run our 420 signal over to our control. Simple to use. So installation is as basic as clamping it into the line. Wiring can be either through a cord grip to the terminal or to an M12 connector, so it can be simply screwing on a molded cord set onto this device, and a very simple startup. Some other aspects. Since we are measuring at the base of refractive index of the liquid, you do need to have specific customized, or I should say specific scales depending on the liquid. That means that if we have a Brix measurement, we have a sucrose Brix measurement, or we could have a high fructose corn syrup 55 measurement or a 42 scale. So we do need to have independent scales depending on the liquid. We simply can't apply one Brix measurement to all products. But we do have those scales available. That's the key. And then the last bit is that we will be able to provide an IRM in a 3-day lead time. So very, very quick delivery. We're going to be building them in Fultonville, or assembling them in Fultonville, and shipping within 3 days of receipt of order. Typical applications, or where we expect that you're going to start to see activity with this. Number one is going to be Brix monitoring. So in this case, this isn't a facility where they're running a process, and what the habit is to have someone drawing a sample periodically, whether that's once every 20 minutes or every 30 minutes. They're pulling that sample and they're checking the Brix to make sure that the product is maintaining specification. Very labor intensive, sometimes they forget to do it, doesn't get well documented, and the application for the IRM is pretty simple, right? We're going to install it into the line and continuously monitor the Brix of the solution or the product that's moving down the pipeline, thus eliminating that human element, which is fraught with errors and cost, right? To have a person committed to always having to maintain this line rather than simply taking it into the PLC, running with set points, and if it's still a manual or ultimately a batch-driven monitoring, we can alarm to go and let us know that our process has a problem, we have to make an adjustment. Now, the second type of Brix measurement, I mentioned monitoring, really looking at replacing a manual exercise that's done in a plant, somebody going over and pulling samples. And the second is going to be direct Brix measurement for control. So in this instance, we may have two streams, let's say most commonly would be orange juice reconstitution. So we're going to work with a concentrated orange juice, and we're going to blend that with water to come to a final stream and maintain a constant Brix. In that instance, we put the IRM into the final streamline and continuously adjust the blend ratio of the water to the concentrate based on the measurement of Brix. So now we optimize that long run of orange juice straight based on the measurement of Brix by an IRM refractometer. Last application that we're going to touch on or talk about will be Play-Doh for brewing. So this is assurance, or I should say this is to determine the sugar concentration in wort. So as we process wort to try to achieve an ideal sugar concentration so that then we can begin fermentation, and that's done either by adding water or boiling off water in the wort kettle to attain that proper Play-Doh. We can use an IRM to monitor the Brix of that, or I should say the Play-Doh in this case, sugar concentration, until we achieve the target. Then we can move forward with it with a repeatable, wort sugar concentration so that our fermentation process also functions properly. So 3 applications to start 3 applications, one being bricks monitoring, trying to eliminate the human element in a plant and replace it with a device that gives continuous measurement. We've seen these kinds of applications with turbidity. We also see that the IRM is going to satisfy that. Second application is direct bricks control, or I should say blending control based on bricks measurement. And then lastly, specific to brewing, but it is wort optimization through Plato control. Next up, so what can it do? What's the range of operation? How much resolution? Because, you know, the first thing you'll ask a customer is, hey, I've got it. You'll tell the customers, I've got a refractometer. They're going to say, great, I've got an application. Here's what it has to do. Well, here's what it can do. I'm going to start off always with a refractive index, and again, that's because that's the basis of operation of this device. So refractive index measurement range 1.330, which is water. So pure water is a 1.330. Just as a data point, a pure vacuum would be 1. So water at 1.330 up to 1.5, which will go up to an 85-degree bricks, sucrose bricks concentration. So a pretty wide band should satisfy the applications that you're going to encounter into a food plant. You know, I don't expect us to be monitoring some of the more larger refractive indexes, which tend to be industrial chemicals. This more so sits around sugar within concentration of liquids. That will be the target, and that will fall well into that 85 and below bricks measurement. So the bricks range of operation that I've got listed there from 0 to 85 is speaking to sucrose just as a basis. So you can see, again, we can go from water up to an 85% concentration of sucrose. Resolution. Resolution is, you know, how many increments can we get? 0.001 for the refractive index. In the case of bricks, that will be 0.05 degree bricks. Precision or accuracy is the same as resolution. So as much as this device can give you in resolution, it's also going to provide in accuracy. So again, bricks to plus or minus 0.05 degrees. Temperature range from -4 to 212 degrees F for process. And then if we have a SIP application where we're going to sterilize, we can go up to 284 degrees F or 140 C for 60 minutes. Lastly, the pressure range on this device is rated at 0 to 300 PSI. The light source, this is an LED light source, and the wavelength is 589.3 nanometers in wavelength, and that's key because in the prior slide I had mentioned the refractive index, and that is based on a specific wavelength of light, which is the accepted standard. And of course, we wouldn't make the wrong decision. Our LED light source is based on the standard wavelength of light. So we have direct measurement of refractive index as the rest of the world sees it. Materials from the wetted side, 316 stainless steel for the fitting. It has a sapphire lens and a fluorosilicone seal to the lens. For the housing, 304 stainless steel, and either a polycarbonate cap, which has a translucent ability to it, or we do offer a stainless steel cap. There is a reason why you may want that plastic cap. If you're wondering why you'd want plastic, is that you can get a status light from this device. The intended approvals will be 3A, so we'll have a 3A approval. That's something I think that most people expect from Anderson these days, and we're not going to fail here. C for environmental, and then CRN, CSA, and BPE. got some of the basics out on what the specifications are. Basically wanted to let you know, where we've got this pin for capabilities should directly map into what our customers will be looking for as far as performance capability. So now I just want to go a little bit down the path of how, where do we put it in the piping schematic, how do we use it? I alluded earlier that we were, this does kind of fit to our ITM line, the turbidity line, as far as it's got a lens, it's got a faceplate that clamps into the line, and we're having that same type of interaction. The only difference is, of course, with the IRM, everything happens at the lens surface, whereas with the ITM, there's a little bit of light penetration into the product stream. So, again, we want to see this in either vertical or horizontal pipelines where the lens is not at the top or the bottom of the line, so that we keep it submerged in the liquid that's flowing through the pipeline. We'll be adamant about it needing a short outlet T, because we need that lens in close proximity to the flow path. So we need that short stub to be washing out continuously and exposing the lens to the product that's currently going down the pipeline. A straight pipeline location, so again, this T somewhere in the straight pipe is the desired, because we want the flow to be more laminar, less turbulent, just because it'll create a little less noise for the operation of the device. We want positive pressure, not to put it on the suction side of a pump, and the reason for that's pretty straightforward. If we go, sub-atmospheric or low pressure, we have an ability for the liquid to off-gas, and any air that's present in the liquid is going to be at its largest size. Whereas if we go into the positive pressure, first off, things like CO2 will stay in dissolved state, so they won't off-gas and corrupt the reading, but also anything that is present just from the process will be diminished because it's going to be compressed. And then lastly, we always like to see the electrical connections pointing down so that the water, flows away from them rather than collecting in them. So counter to the two I just showed you that were the way we'd like to see it, we do not want to see it oriented on the bottom of a horizontal pipeline, and that would be because this sensor, if it was mounted this way, would be prone to collect sediment. In addition, if we were to place the sensor on the top of the pipeline, we've now created a high spot in the line for any air or any gas present to collect. So we want to eliminate those possibilities and avoid this installation at all costs. For wiring of the sensor, we're going to make this is going to be available with two forms of connection. The first one, which we prefer, I think, around Anderson, is the M12 connector. It allows us to provide you a device that's completely sealed as it arrives at the plant, never has to be opened. You can literally just screw the cable on and use it. And in those instances, we're going to have, the 4 to 20 milliamp coming out on the first two terminals, and we'll have a power supply. One thing that's a little different for the IRM versus some of our other, what we would call 4-wire devices, meaning they're not loop powered, they require an external power supply, is that the IRM is going to internally bridge the power supply common with the milliamp common. So we often have to tell people to do that with other sensors to tie together those two wires to run them 3-wire. The IRM comes wired to run 3-wire. In addition to that, if this were to go into an ungrounded pipeline to maintain CE capability, we would ask that the earth ground be terminated on this sensor, and we believe right now that's going to be terminal 5, or in a secondary fashion, if you use our 42117H cable, you'll get that on the shield for the cable, because the nut will carry the grounding of the casing straight through back to the wiring source. If we open up the lid on the IRM, so this is now orienting it up so the fitting's pointing into the screen. What you would see when you took the lid off is a few things. First off, this is going to be a field wiring terminal. If you receive the device, if you purchased it with an M12, there are going to be wires landed on this terminal. You don't have to touch them. You actually don't even have to open up the device when you get it with an M12. However, if you decided you wanted a cord grip because you wanted to field wire this, then you're going to have a cord grip on the electrical connection side. You'll feed in your cable, and you will have to do the terminations of the minimally 3 wires on the terminal strip. In addition to the wiring, this is the status LED, so there is an LED mounted directly on the circuit board, and when we've got that frosted plastic cap, what you'll get is you're going to get some output messaging from the device telling you its status. So you get some visual feedback in the form of a light with different statuses to let you know whether it's operational, in fault, basically letting you know whether it's in a good state or not. Now, in addition to these 2 components, the last thing that is an outward use is a USB communication port. So this is a micro USB, similar that you'd have on your on a phone or on a not on a camera, but on a phone. So it's the smallest USB. You would need to get, and I'm expecting most people will have one of these in their drawer or their backpack, would be a USB, it's a standard USB cable. That's going to be used when and if you want to interface with this with software. Some other application requirements. So these are things to think about with the IRM today, with the fitting that we're going to offer. We feel that most applications are going to be successful if we use low viscosity products. Remember, I've mentioned it a couple times now, the flow must contact the lens. We need to have the flow clearing this lens and putting the most current product that we want to measure up to it. So if we stick this in a dead leg, we're not going to get a good response and we're not going to be effective. So we're thinking low viscosity products are the best to get us that measurement. We need gas-free liquids. Bubbles will affect the measurement. Bubbles will drive the device into error. So this will diagnose them, and it'll stop measuring for us. So we want to make sure the liquid's clear enough so that we can get a good measurement. Another thing, if a scale other than the refractive index is to be used, at the time of order, we're going to want to discuss the product that's being used, the range of operation, and the units of measure. That's under the anticipation that, and I should say, if you're not going to use refractive index or sucrose bricks or Play-Doh for beer wort. So there are going to be 3 selectable choices that you can say, that one will work for me. Sucrose bricks will work, then you don't need this. However, if you're going to do high fructose corn syrup 55, we're going to expect you to tell us, hey, I'm going to apply this. I want to measure bricks of high fructose 55. I need to operate over this operational band, and I want it in bricks. So that would be the expectation so that we can properly process the configuration of the device. Because keep in mind that this unit does not have directly a display to modify, and it only stores a handful of scales within it. All other scales have to be loaded externally. So configuration and maintenance software that's included with the IRM. So I mentioned you'll have to get yourself a micro USB to USB connector to interface this with your laptop or your desktop. After that, there'll be software available on our website that you can download. It's included with the IRM. Install it on your machine, and then you bring it online, connect to the device. You can see the screenshot I grabbed. It was connected on my desktop at the time that I was taking the screenshot. And under this, I now have the ability with the sensor. I could go and create this drop-down of scale 1 is bricks, currently configured for that, and I could hit the drop-down and select it to read out in refractive index, or I could select it to read out in Play-Doh. I can also affect the units of temperature measurement and the dampening of the device. Going a little further, what the last screen gave you is what shows up front, but we do have a series of drop-downs also associated with this. So let's say you didn't get the correct scale for your device and we had to do a retrofit. We would have the ability through the software to load a scale onto the device. In addition, there is the ability to affect a field calibration test on the either pure water or on a standard. So now getting down to the configuration of this device. So you can see this is a nice short matrix. I like short matrices, especially when half of them are filled out at the beginning. So we have an IRM11 that we know and a TC2. So at this time, only a TC2 2-inch tri-clamp is available with basically a flush front on it. Then we'll select the surface finish desired. So if we're doing a typical food application, I'm sure 25 RA will be suitable. If we did want to go into a BPE, 15 RA is going to be available with an electropolish. Next would be scale selection. So even though this is available, the top three are available when you get the device and you can configure freely amongst them. You can ask us at the time of order, you'll put the request in on how you want it to arrive. And the reason for that's simple. If you make that selection, when this unit arrives at your plant or at the customer's plant and they're going to install it, they don't have to do anything. They simply clamp at the line, screw on the M12, and use it. If they don't, they're going to have to install the software on their machine, they'll have to plug into the cable, and then they'll have to select the scale that they want to use. Either is their choice. Again, bricks is a sucrose bricks. Keep that in mind. So we are talking about, not talking about high fructose corn syrups. We are talking about sucrose as the base. And the Play-Doh is wort-based. So this is, again, brewing wort. Right after we do our mash and clarification, we're going to cook our wort. This is for measuring the sugar in that wort. Pre-fermentation. The second fermentation starts to occur, the rules change on what we're measuring. This last line, XX, is consult factory, because what we're going to have is this is when we're going to go into something special. If you told me you wanted an IRM and you wanted to do salt concentration, we would have to develop a special curve and program it into your sensor. That's how we'll use this line. Next up, electrical connection. The choices of M12, cable gland, or NPT, half-inch NPT. Again, we favor M12. This is how we want to see it, because we know when the device arrives, it's watertight, it's already impervious to your environment, and we know it'll stay that way. If we go with cable gland or half-inch NPT, we're at the mercy of the electrician to do the best job possible to seal the internals of this device. You know, we're starting with a price tag of $12,000. We don't want this to get flooded, so I can't recommend the M12 enough. And then lastly, the cap. So I mentioned about the opaque plastic. With the opaque plastic, you do get the status light, so you get a visual output from this device letting you know how it's functioning. However, if you've got a really hostile environment or people who like to beat on plastic with hammers, we do have a stainless steel option. However, if I've got people that are beating on $12,000 refractometers with hammers, I want to rethink who's working for me. So to summarize on what we've got, we should be seeing the IRM up on the website within the next couple of weeks. Shortly following that, we will be able to take orders. Next 2 to 3 weeks, we should have it in our system so that we could start entering orders, and we expect to have shipments in early July. That's the current plan. Again, from the product side, what makes the IRM special? It's very simple to use, right? This is literally plug and play. It's all integral, so it's not two-piece, doesn't require configuration and a lot of startup commissioning work. customizable scales available for specific products. So if we do that little bit of work in the beginning, again, we can make it simple to install, but we can also make it work very well. And then lastly, short lead time, 3-day target. So in small quantities, 1, 2 devices, and standard scales such as refractive index or bricks, we can deliver in 3 days. That's our target. And with that, I'm going to open up to questions. First question I've got is, how big does a brewery have to be before they consider a Plato measurement? And I think there's 2 components to that. It's not just size. It is a function of how sophisticated or how interested in quality are they. Because what it affords is the ability to produce a wort that is at a very specific, repeatable concentration, which then allows the rest of the process to very clearly follow it. So it's definitely not going to be your local brew pub, but it doesn't take too much before an individual, if he's successful, wants to start to get to a consistency and quality level in his product. Any other questions? The question is, this will compete with NIR, specifically Optech. The statement is, this is refractive index measurement. So it is going to do direct measurement of dissolved solids in a liquid. Specifically, the target will be bricks for starts. Got another one. Can I use the IRM for phase transition? Yes, you can if your interest was in dissolved solids. So if you were in a situation where your concern was that you're throwing sugar down your drain or you're not recovering all your product and it's an expensive sweetened product, you could use this for phase transition. It's an expensive solution for it, but you could use it. Any other questions? I've got one. How do I rescale the output? I'm going to try to interpret this. If we're saying, how do I change the range? The answer will be, you will have to send in a different scale. So the scale that's downloaded into that sensor is what specifically sets up the range of operation. In the same breath, if I wanted to take a standard sensor and I wanted to rescale it for a different product, you would also have to download a new scale. So that would then require a conversation with us over at Anderson-Negele to go and find out what it is you're trying to do, have a new program created, or I should say have a new scale created, and then figure out how to get that into your device, whether that was done in the field or internally. Any other questions? All right, well then I guess I'm going to call it. Thank you all for attending and have a great weekend.